How is the duration of bare ice and other factors impacting the darkening of the Greenland ice sheet? Hello, friends. Jim here. In a paper published in Geophysical Research Letters, part of AGU, the impact of bare ice duration and geotopographical factors on the darkening of the Greenland ice sheet. The lead author is Shunan Feng, a whole bunch of other folks, published towards the end of 2023 in December. So let's look at the abstract. Dark, low albedo surface ice on the Greenland ice sheet enhances melting and subsequent runoff, a major mass loss contributor during the ablation season. The accumulation of both biological, for example, glacier ice algae, and abiotic, for example, mineral dust, light-absorbing particulates are important darkening factors that are potentially influenced by the duration of snow-free bare ice, phenological factor, and other geotopographical factors such as elevation, slope, aspect, the distance from the ice margin. Here we present the first medium resolution 30-meter analysis of the phenological and geotopographical controls on the distribution of dark ice in southeast-southwest Greenland, from statistical analysis of data derived from a harmonized satellite albedo product in Arctic DEM. The duration of bare ice primarily controls the distribution of dark surface ice, allowing for algae growth on inland ice surfaces in particular, whereas geotopographical factors are only secondary controls. So what are the key points? The duration of snow-free bare ice is the primary control on the distribution of dark ice. Longer periods of bare ice, medians about 40 days, are prerequisites for ice to become dark. Surface slope and aspect influence darkening by modulating the duration of bare ice and glacier ice algae growth. So the plain language summary. Meltwater that runs off the Greenland ice sheet is currently the largest single glaciological contributor to global sea level rise. Recent darkening of the surface ice has contributed significantly to increased melt rates. We use medium resolution satellite data to link ice surface darkness, albedo, to the topography, elevation, slope aspect of the ice sheet surface, the distance from the ice margin, and the duration of bare or snow-free surface ice. Our analysis shows that the duration of bare ice or snow-free conditions was the most significant factor in driving the darkening of the ice, and hence by implication, the rate of meltwater added to the ocean. We also found that the impact of topographic factors on the ice darkening varied depending on whether abiotic or biological processes were driving the darkening. Okay. Now, before I go any further, I thought I would spend a few minutes discussing what is meant by ablation, right? We saw this term up here, the ablation season. What is ablation? Well, let's take a pop. Glacier accumulation and ablation. This occurred on antarcticglaciers.org. Okay. Glacier accumulation. A glacier is a pile of snow and ice in cold regions, poles or high altitudes. More snow falls, accumulates, then melts, ablates. So basically, ablation is referring to melting in the summer season. A little more complicated than that. If the snowpack starts to remain over the summer months, it will gradually build up into a glacier over a period of years. So glaciers as a system, a little diagram to help us picture this. So what are the accumulation inputs? Precipitation, rain, hail, freezing rain, snow, right? Other sources: wind-blown snow, avalanches, right? Hoarfrost. Hoarfrost is a specific type of frost that we typically find in like when there's really some like snotty conditions present. For example, if you look at the observatory on top of Mount Washington, it often has a buildup of hoarfrost and so on. So all these are inputs that will allow for surface accumulation. Well, this thing called gravity. So all this thing starts to flow downhill. Right? So you got this glacier flow downhill. And you got processes such as abrasion, moving debris, deposition, transport, so on. So what are the outputs? The ablation, wind-blown snow. So you can have wind-blown snow at elevation, higher elevations to accumulate the snow, and then it slides down to lower elevations, and that same wind can blow the snow away. The point is before it gets a chance to compact into ice. Maybe even have avalanching. Sublimation, that's going directly from the solid to the gas state. Surface meltwater runoff, subaerial melt and sublimation. So the outputs of meltwater, icebergs, landforms such as moraines, And then you have internal basal melt, right? And then should you have a water terminating glacier, you can have calving and subaqueous frontal melt. Okay? So that's what ablation is. It's basically the loss of the ice and snow through various methods, not just simple melting. So it's a comprehensive term. The glacier loses mass, ablates, mainly by the processes of calving, surface subaqueous melt, and some wind activity. All right, ice, you have snow falls, it accumulates, it persists, it compacts, it builds up. Glacier ablation. As ice flows downhill, it either reaches warmer climate or it reaches the ocean. This causes various processes of melt or ablation to occur. In land terminating glacier, basically it ends on dry land, the main processes of ablation will be surface melt. Because, air temperatures kind of go up as you go lower in elevation. This meltwater runs off the glacier and forms a number of rivers that typically drain the glacier. And they show a nice little meltwater stream, Mendenhall Glacier, Alaska. That's in Juneau, outside Juneau. The surface meltwater may run off a surface runoff. This is supraglacial meltwater stream on the surface, or it may make its way to the bed of the glacier through cracks. The water at the glacier bed eventually makes its way to the margins of the glacier where it exits as meltwater stream. So it worked its way through these crevices or crevasses and eventually makes its way down to the bedrock where it can flow out. That can also serve the purpose of lubricating the base so that the glacier moves. And then you get these little lakes called moulins up on the surface that can also let the water, drive its way through. Glaciers that reach the sea or terminate in a lake, moraine terminating and lacustrine terminating, respectively, additionally will calve icebergs and melt on the water. The lower part of the glacier generally loses more mass from ablation than it receives from accumulation. This part of the glacier is the ablation zone. And we can look at the equilibrium line altitude. Most glaciers receive more inputs and accumulation in their upper reaches and lose more mass by ablation in their lower reaches. The equilibrium line altitude, ELA, marks the area of the glacier separating the accumulation zone from the ablation zone, and where where annual accumulation and ablation are equal, hence the term equilibrium. So you got the accumulation zone, you got the ablation zone. Here's the equilibrium line. Or diagrammatically, it accumulates, and then you have the ablation zone. So upward thickening, downward thinning, and where the rates are equal, the rate of accumulation equals the rate of ablation, the rate of loss, that's the equilibrium ice flow. Okay, so hopefully this gives you an idea what's meant by ablation and what we're going to be talking about in this paper. So back to the paper. In the intro. And by the way, I'll leave the URL in the comments and in the description of the video. Mass loss from the Greenland ice sheet, abbreviated as GRIS, G-R-I-S, is the largest single cryospheric contributor to sea level rise, according to these researchers. Mass loss has increased sixfold since the 1980s. Accounts for 25% of global mean sea level rise. Surface albedo is a critical parameter that modulates the absorption of solar radiation by the ice sheet. Recent darkening of GRIS enhances surface melt, increases the growth of dark pigmented glacier algae, which further darkens the surface ice, increasing the melting, referred to as bioalbedo darkening feedback. Dark ice is unevenly distributed around the GRIS, but a band of surface ice with especially low albedo appears annually in the ablation zone of the southwest GRIS between 65 degrees and 70 degrees north latitude. It's known as the dark zone, DZ. The positive feedback between meltwater production and darkening accounts for approximately 40% of the annual mass balance change in the dark zone. The area of the DZ varies annually, includes ice spanning from the margin to elevations above. And 1,100 meters, and I think ASL is actual sea level or adjusted sea level. Bioalbedo feedback is a major darkening mechanism within the DZ. It's likely to be highly seasonal and stronger in longer summers because of its biological component. So they show here the map of the study area and some of the sampling points here. So let's see if we can enlarge this. So the map shows the average summer, July-August snow-free ice albedo in the study period, which goes from 09 to 17. Contour lines are generated using appropriate software. And the dashed line shows the average snow line. Let's see if we can increase. There we go. So we basically seeing where they're doing their work here. Here's the 2,000 meter line above sea level. So above sea level. Here's the southwest. So here's showing you the sample locations. And there's the snow line. And they show the albedo. And as you get towards the purple and the really deep purple, you get lower albedo, which means less reflectance. So as you can see, it's pretty coastal, even going further north. Now that's what that shows here. Other processes may also explain the darkening of the GRIS and the formation of the DZ. Tedesco in 2016, along with others, suggested that the darkening of the entire GRIS is driven by increased air temperature, retreat of the snow line, accumulation of meltwater, as well as light-absorbing particulates, or laps, in the surface ice. These laps include dust derived from dry deposition of contemporary atmospheric aerosol, melt out of old dust from outcropping ice, or just plain dust in the atmosphere that makes its way to there. We can also have black carbon, glacier ice algae. The accumulation of laps in the bioalbedo feedback amplify ablation and explain more than 70% of the spatial variability of albedo at regional scales. Okay. As said, I will leave the URL for those who want to read the article in all its detail. The duration of bare snow-free surface ice is believed to be a key factor influencing the biological darkening through algae growth in summer, and is hereafter referred to as a phenological factor. This is strongly correlated with the mean air temperature in July, since the average surface albedo is closely associated with the migration of the snow line to higher elevation, which exposes more bare surface ice. Here we aim to investigate whether the regional and local distribution of dark ice in the southeast and the southwest of GRIS can be explained by the simple phenological other geotopographical factors. Remember, when you form ice, okay, depending on the level of freezing, it's pretty much translucent or at least opaque. And you put snow on it, it acts like an insulation. Well, if the snow melts back, or you remove it somehow, now you're actually looking at the actual ice. And if there's anything like the algae, particulate matters, and so on, that can help, because the albedo is reduced, it absorbs the heat energy and can increase the melt rate, the ablation rates. All right, they go through a section of explaining the methodology. Again, I'll leave that for you if you care to check it yourself. Figure 2. Associations between A and B, albedo and elevation. So that would be A and A and B right next to each other. Okay. Associated between A and B, albedo and elevation. D and E, slope. Okay. G and H is aspect. J and K is the distance from the ice margin. M and N is the snow-free duration. Blue dashed line indicates the threshold, which is an albedo of approximately 0.45. That threshold separates the bare and the dark ice. The distributions of each factor are shown in the box plots to the column. Ice classes are indicated by colors in the box plots. So let's see if we can enlarge this. All right. I'll enlarge this and just scroll down as need be. Okay, let's see if we can make that even a little bigger. Okay. So we see that, generally speaking, right? So we on the left column is the southwest, and the right column is the southeast locations. Okay, and they're taking the log of the count. That's what these numbers are. The 1, 2, 3. That's the log. It kind of linearizes it. The blue dashed line is that the albedo 0.5. That's the transition overall. And as you can see, the albedo increases as you increase in elevation, especially for the southwest. It's still increasing in the southeast, but not as much. It has a lower albedo. And we can see the box plot. So the box itself is the interquartile range. It's from the 25th to the 75th percentile, 50% of the data. This line here would be the median. Then you have the low and the high values. So blue is bare ice, brown is dark ice. And for Southwest, you can see what the values are. Looking at the albedo when looking at how slope, what's the degree of the slope. And generally speaking, that the flatter the slope is, the higher the albedo. And the box plots are really interesting, kind of really very small interquartile range. So you can see there's a lot of, I would take these to be outliers. And the other one I find of interest is the distance. Basically, we can see that albedo decreases with increasing distance. So basically, the overall message or info trying to be relayed here is that albedo increases with an increase in elevation. It increases the flatter the slope is, and it increases. This seems to be the the further, further inland or that one goes. So dark ice is more prevalent in the Southwest, with 37.5% of sampled ice pixels being dark ice, compared to only 25.2% in the Southeast. Figures 2A and 2B, I guess, is this here. The majority of the Southwest dark ice interquartile range, IQR, falls in the elevation range of 673 to 1,214 meters above sea level. The median is 1,013. This is 5 meters higher than the median elevation in the Southeast, 1,000 meters higher than the Southeast upper quartile. The bare ice median elevation is higher than that of the dark ice in both regions. Generally, slopes in the Southeast are steeper than the Southwest, and the slopes containing dark ice are steeper than those of bare ice. And they used a Right-tail-Wilcoxon rank sum test, p-value of 0.001. And in case you're wondering, Wilcoxon test is a statistical test that's used for non-parametric distributions, where the population does not necessarily have what's called a quote-unquote normal distribution. So that it's a rank test that's used for such situations. The snow-free duration of bare ice in the Southwest is statistically longer than in the Southeast. The median dark ice elevation is lower than bare ice for both the ice at the margin and inland. Slopes of dark ice are steeper than bare ice at the margin. However, inland ice surfaces are mostly flat. The distribution of aspect at the margin and inland differ. Dark ice aspects are statistically smaller than for bare ice at the margin, but greater inland. So figure 4 presents a distribution summary stats for elevation slope aspect. Okay, so what's of noteworthiness to point out in the discussion? Snow-free duration is the most critical factor. That's figure 3, which is this, right? So the importance, right? You can see elevation, distance, right? duration. And then by the south, then they do a pie chart for the southwest. So let's see, 29% looks like it's elevation. Duration, 31%. So that's the largest pie. And then for the southeast, it looks again, duration appears to be the main factor in determining, what happens with ablation. Snow-free duration is the most important predictor in both regions. Elevation is the second most predictor, followed by distance from the ice margin scores and the slope. So, snow-free duration is most critical. Longer durations give the biological component of lapse, right, the particulates. Glacial ice algae more time to grow. Meltwater and the abiotic components of lapse, dusk, cryoconite, and black carbon may also accumulate as the melt season progresses. We hypothesize that the presence of algae helps to aggregate and retain abiotic impurities due to their production of cohesive compounds such as extracellular polymeric substances, which in turn reduce surface albedo, generate more melting. Snow lines are projected to retreat into the flatter ice sheet interior under warmer climates, unless offset by enhanced winter accumulation. Our analysis also suggests that future expansion of the bare ice area and prolonged snow-free duration may induce a rapid expansion of dark ice distribution, causing positive feedback resulting in even more surface melt or increased ablation. Spatial distribution of dark ice is limited to the ice margin in the southeast, while the dark ice can extend up to 50 kilometers inland in the southwest. The areas below the average snow line make up about 23.6% and 21.8% of the total area of southwest, southeast, respectively. Geotopographic factors play a secondary role in regulating the distribution of dark ice, although elevation, surface slope, and aspect may influence the snow-free duration. Generally, snow-free duration decreases with elevation, but we note that dark ice in the southwest occurs at higher elevation than the southeast. The influence of lapse is more crucial on south-facing slopes than on flatter surfaces because the ice receives more intense solar radiation. Makes perfect sense. Okay, so what are the conclusions? The darkening of ice on the grist results from a complex combination of abiotic biological processes, geotopographical factors, elevation, slope, aspect, and the distance from the ice margin. Results reveal that the snow-free duration is the primary factor governing the darkening of surface ice, enabling lapse meltwater to accumulate, increasing ablation, increasing melting, increasing ice loss. Climate forcings regulate the extent of snow-free ablation areas, making room for new bare ice to darken. Geotopographic factors are secondary controls. So, a lot of interesting analysis taking place in here, but the main take-home message from all of this is that we have factors that contribute to the darkening of the ice, to the creation of more bare ice that allows the darkening. And what this happens is that the algae can darken, there'll be accumulation of atmospheric particles that decrease the albedo, increasing the heat absorbed, increases ablation rates, which translates as increased melt rates, which leads to increased ice loss. That is what's happening here. All this stuff here, all these things here that I try to go through and explain for you can be summed up that dark ice enhances melting, subsequent runoff. And this dark ice can result from biological and mineral dust. And if you have processes that remove the snow, that then contributes to the darkening of the ice, lowering the albedo, increasing ablation, increasing melt rates, increasing ice loss, leading to increased sea level. That's the take-home message. Well, I hope you found this interesting. I hope I did not confuse the crap out of you people too much. I thank you for your time, and we'll talk soon. If you stuck around to the end of the video, thank you for watching. Be sure to give this a thumbs up, as it really helps the channel. And if you can, please support me either on Patreon and or buy me a coffee. Details in the description box below. Thank you.